research interest in subjects like star formation history, galaxy evolution, Asian supermassive black holes, FRBs, and he also worked on outreach, being active on YouTube, talking about astronomy and sci-fi topics. And today we'll hear him talking about cosmic star formation history with JWST number counts. Let's welcome Tomo.
Thank you, Ida. Thank you, everyone, for coming to my talk. It is my pleasure to visit Academia Sinica after COVID-19. It's been probably 3 or 4 years, so it's very good to see many familiar faces or new faces. Today, I want to introduce my students' work. So I show some of my students' pictures here, but I hope I can convince you that even undergrad students can do good science with JWST data. Okay, so let's get started. I want to start with the question, what is JWST for you? What is JWST for you? Some people say it's a lifetime dream, or some people say just a telescope. It's very researcher-like answer, or successor or Spitzer. But for me, JWST is 10 times larger ASIAA space infrared telescope, and I tell you the reason later. So let's start with a little bit of history. Then I've been working with the ASIAA Space Infrared Telescope for the last more than 10 years. ASIAA was 65 centimeter infrared space telescope that's inside here. They launched with Japanese M5 rocket. Then, here's a launch movie that every time I showed in my talk. So launch. Then it did the all-sky survey in mid and fine infrared, and then also a very deep survey in the MEP region in mid infrared. So that's what ASIAA did. And then and the purpose was, using infrared, we want to catch the dusty star formation or ASIAA activity. And then one of the unique features of ASIAA Space Telescope was it had 9 continuous mid-infrared filters. So this is mid-infrared, 3 to 24, 5 micron. And as you can see, Spitzer had a very large filter gap between here and MIPS 24. So if your favorite emission line falls into the gap, there was not much you can do. But ASIAA, and the Y was similar, Y had the filter gap too, but ASIAA was continuous filter, so wherever, say for example, you want to observe the pH emission lines, which is a good indicator of star formation activity. And then in case of Spitzer, if the pH emission falls into the gap, there's not much you can do. But in case of ASIAA, whatever redshift is your galaxy, one of the filters, because filters are continuous, one of the filters can capture directly the pH emission here. Or if it's at redshift 2, it's going to 24 micron filter. So that was one of the unique features of the ASIAA. Okay, and then taking advantage of this filter, we worked on the say 12 micron luminosity function. This is infrared luminosity function. It shows very steady evolution from low redshift, high redshift. This evolution, and then we also integrated. We can do LCD fitting with 9 filters, and that's more accurate than 4 filters of Spitzer. We have 9 bands, so that's more accurate. And then we did the total infrared luminosity function that also shows a very steady evolution from here, low redshift to high redshift. And then we drew something like this, creating Madao plot, cosmic star formation history. Infrared luminosity density, which can be translated to star formation rate density as a function of redshift, and it shows a steady increase about 1 order from redshift 0 to redshift 1 or 1.5. So that's what we did with a ASIAA telescope with 65 centimeter mirror. But with the 65 centimeter mirror, of course, we had a limitation. We did the cosmic expansion rate, but we're only looking at the brightest galaxies, ULUX or LUG. We're not looking at the faint galaxies. And then, when I say high redshift, it's redshift 1 or 2. We're not going any high redshift. So that was the limitation of the 65 centimeter mirror. Okay, then next thing we're planning is, we need bigger telescope, and then and also a lot of colleagues at Academia Sinica was working hard to make SPICA 2 or 3 meter telescope happen. But as you know, unfortunately, it didn't happen, so we're crying. But then suddenly, this year, this NASA helped us. They made a telescope. You take a good picture? They made the Akari telescope 10 times bigger. So that was a very lucky situation for us. Then the reason I keep saying that JWST is larger Akari, JWST is 6.1 meter mirror, so it's exactly 10 times larger than Akari, is its similarity in mid-infrared filters. So these are Akari's mid-infrared filters, and these are JWST mid-infrared filters. And as you can see, JWST filters also covers the mid-infrared range nicely, continuously with 9 filters, just Akari did. So this is also lucky situation for us. So whatever the code or script or analysis technique we developed for Akari for the last 10 years, we can just use it for JWST data, and then we can write new papers. So that's why I keep saying for me, and JWST is 10 times larger Akari. Okay, then also JWST is like a very very generous policy, public. In addition to early release observatory, which was immediately public, and also large surveys such as CSFH or Primer, those surveys make their data public immediately. So that's everybody, including us, for analysis. So that was very nice of them. So there's a big chance here. So that it's like a base are loaded and the next pattern is alternate. So that kind of big chance is coming. So as a researcher, I cannot miss this chance. That's what I feel. Okay. Did you guys see baseball? Maybe not. Okay. Okay. Then, however, there's a problem. So I'm at the Seyfert University, and then NASA doesn't give us, a lot of postdoc and a good PhD students. Most of the students I have is undergrad students. And then they ask me amazing questions like, what is PSF? It's not like PlayStation 5, it's PlayStation. What is magnitude? This is, very common question. I cannot with fast Excel. So these are the undergrad students that I have to work with. Well, they are smart, but they just don't have a background. Okay. Then, and then what can we do? What can undergrad students do with JWST? They did. And then the answer we came up is galaxy number count. Okay. Galaxy number count is very simple. It's just a counting number of galaxies as a function of flux. So that's basically making one histogram, right? So that should be easy enough for undergraduate students to do. Well, still, it's a fundamental statistics, still carry information on galaxy formation and evolution, so it's still useful. So we tried this galaxy number count with my cute students. So data we use is a JWST data. It's in Stefan's pointed field, because this field is large after, this background is Stefan's pointed field. And of course, we remove these big galaxies and we use these empty area to study background galaxies. And then also Shearer's field, which has 4 MIRI pointings. Okay, and then, I said it's just a counting number of galaxies, but we did the basic thing. Our student did the basic thing. So this student, Jimmy, we did the background subtraction, source extraction ourselves because we found the official catalog that they released missing a lot of sources, so we did the source extraction ourselves. And then we need to measure the completeness. So he put artificial sources to the JWST image and then many times, and then measure the completeness. So this is a completeness curve in each filter. And then we use the data to the depth of the 80% completeness. So that's what we did. Also, we did the reliability test. So we flip the image, positive and negative, and then test how many spurious sources are there. And then to the limit that we measure the data, the data are almost 100% reliable, meaning very few fake sources in the data. Okay. Then the number counts he did is something like this. So this is Stefan's quintet field, and this is 7 micron, 10 micron, 15 micron, and then these are data points from JWST. Let's because the plot is small, so let's zoom into one of the plot. Here I'm showing 15 micron JWST number count, and then here before JWST, these are number counts from ASIAA or Spitzer Space Telescope. And as you can see, these number counts are in a MIRI range. But JWST data are here. So these blue ones are JWST data. And as you can see, these JWST number counts are going into micro Jansky level. So about here from here, 2 orders deeper than the Spitzer or ASIAA. So that's the power of the 6.5 meter mirror. And then he actually worked very quickly. So the data, as you know, was released last year in July 12th, right? July 12th. And then he submitted in a month or so, and then that paper was already accepted in September. So that was well done. So this is his paper. This was maybe one of the first JWST paper from Taiwan. So, okay. Question? Yes, please.
So, how do you do star-galaxy separation?
This is including both. Just number count. I'm not separating. So actually, that's a good point. So 7 micron. If I look at the 7 micron, well, okay. 7 micron. There should be maybe a little bit contribution from star in a bright flux, as you know. But JWST count is very faint here, so already star's contribution is probably less. So this curve, these are Spitzer and then ASIAA. These curves they remove stars. If you don't remove stars, this continues to go on. Because at the bright flux, there are stars. But JWST comes from here, so actually the contribution from stars are probably very small already here.
And so I think since the first release of data, there is some improvements in the photometric calibration of the instruments. So since you got this published right away,
right?
Are there concerns of calibration?
That we haven't looked at it. The students are looking at new data now. Actually, another student is looking at the new data now. Then we should check it over there. Okay. Then, okay, that was good. And then another student, Kosas, he was looking at the shears field. That's another data. And in this field, MIRI inferred instrument have more filters, 6 filters. So he did 7, 10, 12, 15, 18, 20 micron number count. And then let's zoom into again one of the wavelengths. So this is 7 micron. And then again, this is ASIAA and Spitzer. And then JWST, he analyzed its heat. Again, this ASIAA and Spitzer was in the mini-Jansky level, but now we are going to the micro-Jansky level number count. So it's interesting. There's almost no overlap between Akari and Spitzer. It's just perfect timing to perfect flux to continue the number counts to the fainter end. So that's the number count. Okay, and his paper is submitted, but he's working on the referee's report. Okay. Now, so that was good, the 2 papers submitted, but experts sitting here might be thinking, okay, it's just number counts. Is there anything interesting? Anyone can do it. I can do it easily. It's just making histogram, right? It's boring, isn't it? One, did you think you just thought it's boring, right? Oh my God. Okay, so I agree. So it's very simple statistic. So what's important is how, it's good and bad. It's very simple statistic. So not, world expert wants to do it, right? So there's an opportunity for my students to write paper. That is good. But then it's also true. It's important for us to learn physics. Just showing plot is not the final purpose of our research. We need to learn about galaxy evolution and then formation, right? So how do we get this information about, for example, cosmic star formation history is important. So here, usually when you have a catalog, new galaxy catalog, this is how you do the cosmic star formation history. So you calculate the photology and LCD fitting, and then get the luminosity of each galaxy, and then correct for volume effect, then get the luminosity function, integrate luminosity function, cosmic star formation history. That's what usually normal people do. But this is too difficult for undergrad students. They cannot do it. Photology, LCD fitting, luminosity calculation, that's too much for undergrad students to do. And in principle, also, not all the field has optical near-infrared data. Not all the near-infrared field have optical near-infrared data. So, in principle, those fields need more data to do this. So, instead we took a model-based approach. So, that's what I'm going to explain now. So, model will count the JWST data. That's what we did. What I mean is, so we put some assumption and function shape introduced here to get physical information. So redshift 0 luminosity function shape. These are measured by this paper, Gruppioni 2010. So it's like this Jeffter function. So they're measured already at redshift 0 luminosity function shape. Okay? Then we parameterize its evolution using this kind of function. So here, 3 parameters here. A for luminosity, A is a normalization for luminosity and also number density. And then this omega and kappa decides the functional shape of the evolution. And then these decides the luminosity and the density evolution, which is needed here and here for luminosity function. So if we parameterize luminosity, its evolution like this, and then decide these 4 parameters, we know the evolution of the luminosity function. So that's the functional shape that we assume. Okay, and then we do this, for 5 population of representative galaxies, which is I showed here. So these are type 1, type 2. This is maybe too small, but type 1, type 2 AGN, and then starburst, composite, and then normal star forming galaxy. So SED shape or something like this. And then so 5 population of galaxies, and then each one has 4 evolutional parameters. So we have 20 parameters. Okay. Then if we decide 20 parameters, then we know the evolution of the luminosity functions. Okay. If we decide 20 parameters, we become God, right? We know everything about the universe. Okay. So that's what we want to do. What I know that we being God is here. So once we decide those 20 parameters, we know the evolution of luminosity function in all wavelengths. say, for example, this is 50 micron luminosity function wavelength evolution. Well, but this part is my postdoc Songjin Kim is working on. Then we know the luminosity function evolution. So once you decide those parameters, say the AGN luminosity function evolution from redshift 0 to 3 or 4, peak at 3 or 4, and then goes down again towards higher redshift, maybe redshift 680 is here. So that's, we know that from those 20 parameters, and then we know that for 5 population of galaxies, starbursts is like here, redshift 0 to 3 and 8, something like that. Okay. And then, if we know the luminosity function, then we know the number count, contribution to the number count from each particular redshift, each population of galaxy, right? So for example, this is showing 50 micron contribution to 50 micron number count from each population. They look at type 1 Asia, and then so these colors are redshift. So from redshift 0, contribution something like this, redshift 4, contribution something like this. And then of course, if you integrate over the redshift, you get the overall contribution to the 50 micron number count. This is number count, right? This is the number as a function of flux. And then we have 5 populations. So if we add up all contributions to the 50 micron number counts to the if you add everything, then we get the overall 50 micron number counts that should be observed by the JWST. Okay, so now what we need to do is, like, if we decide 20 parameters, we get observed number count. So we need to decide, we fit this to the observed number count to decide these 20 parameters, and that's what we did here. So now those red points are JWST number counts in each JWST filter, 6 JWST filters. And then Songjin here discount this red curve is the best fit curve to decide this 20 parameters. So he fit the observed data by changing these 20 parameters, and then he decided the best fit parameter. Okay. And then now we know the best fit parameters for the 5 populations of AC populations of galaxies. Now we know everything, so we can integrate that. So now we have luminosity function, so we integrated that, and then we get the cosmic star formation history. So by integrating luminosity function, we get the inferred luminosity density that can be translated to cosmic star formation rate density, and this red one is the from the JWST data we get. And then, okay, maybe it's so the other colors, like those blue, black, yellow, are from other work, like UV work using Hubble or JWST or previous Spitzer, and then, well, mostly we agree with previous work. Okay. Then maybe you're thinking, maybe Wilson's thinking, oh, you just agreed with previous work. That's not very interesting. But please remember here, the previous work, especially infrared work, were mostly only using U-lugs and lugs, right? But then our data are 2 orders fainter. So, and then previous luminosity function, they usually extrapolate to the fainter end because the faint galaxies are not detected in 65 centimeter previous telescope. But our work, we detected more fainter galaxies like 2 orders to decide this curve. So I think it's good to just really detect fainter sources and then reflect in the cosmic star formation history. That's, I think, the improvement in here. Okay. Then, so this part is only doing. So we assume SED, right? So for each SED of 5 different populations, Okay, so we assume these 5 different SED population of galaxies. And we know for each population of galaxies how much contribution from AGN. Well, basically, type 1 and type 2 AGNs are mostly AGN, and a deep starburst galaxy, there's no AGN. But we know how much contribution AGN. So we can separate these two. And then actually, this part is excluding AGN contribution in infrared luminosity density. So if I plot just AGN part, this and then contribution from the other, then we can get AGN's accretion history of the river. Well, this is still preliminary. We're trying to understand, or understand why we have a little bit offset from different works. It's probably a difference in the methodology, but we are trying to finalize it. But that's something we are trying to do. Okay, how am I doing? Time for time.
Still have plenty of time.
Okay, good. Okay, then that's the main part of my talk, and I want to talk about a little bit what ongoing work that other students are doing. So this is another student of mine, Poya is doing. He is trying to find a new brown dwarf in the JWST data. Okay.
So can you go back? I mean, you
Sure.
have 20 parameters. There must be degeneracies. And
Right.
what's the model uncertainty in your record?
Okay. Uncertainty is plotted in this shaded region. This cross region is the errors of the parameter. About the degeneracy, that Songjin is working on MCMC to calculate the degeneracy, but he hasn't finished it yet. So,
Are those red axes the uncertainty in your model?
this uncertainty is here.
Right,
So,
okay.
so this is our curve, best fit, and the uncertainty is something like that. What happened? I stopped the slideshow. Okay.
Yeah, so my follow-up was, shouldn't it go more uncertain when you increase the redshift?
That's a very good question. Yeah. Why the uncertainty is smaller here? That's because we assume the functional shape. So this shape, overall shape, it's sort of decided by our function. We're sort of fitting this width and a normalization, and then where is the peak? That's what we are fitting. So that's why this part is actually decided by this functional here.
I'm just curious, so you mentioned that this is actually consistent with previous measurement based on bright sources. So can I say that the fainter sources, they are actually not contributing a lot to the total star formation history or total star formation activity of the universe?
Well, to be more accurate, the previous extrapolation was not far off.
Okay, it's consistent with,
Right.
okay.
Right.
Thanks.
Okay, then I want to talk about another student's work. She's looking for brown dwarf with JWST, and JWST is actually very powerful for finding brown dwarf. So just a small introduction. The brown dwarf is something between planet and star, and then atmosphere, gas band, exoplanet, constraint theories of star formation. You can probe the low mass limit of star formation. Well, these are the scientific motivation, but brown dwarfs are important. Okay, then what's nice about brown dwarf is JWST's filters. So these are JWST's near comes the filters, right? This is not mid infrared, this is near infrared. And then they have this 2.7 micron filter, and that is very, very good. So then the brown dwarfs, when the temperature goes down, then the more complicated molecules can exist in the atmosphere because of the low temperature, right? Then if the temperature goes 1000 K or below, then there will be this water molecule absorption in the atmosphere becomes very, very significant. So So this is a sequence of the temperature. So as temperature goes down here, 2.7 micron absorption gets bigger and then bigger and bigger. And then JWST has a right filter right there. So that's perfect to find the brown dwarf. And then, so she came up with, she actually modeled the brown dwarf's color. So these are these are normal. These are brown dwarf color by model. This green one is similar current model. She integrated by combining the JWST filter, and then she selected object in this area. She selected point sources in this area. And then she found one brown dwarf here, this red one. This is 2 micron to 4 micron color, so it's bright in 4 micron and faint in 2 micron. Just like you can see here. 4 micron, there's not much absorption, right? It's bright and faint here. So that's what she found. And then this is the object she found. So these black points are photometric points from JWST. By the way, this is combining all the fields, shears and then glass and then Stefan's quintet, all the fields are LEDs observation. Then this is photometric data points of JWST, and as you can see, this 2.7 micron is very faint, right? Perhaps because of the water absorption. So that's probably very different from galaxy spectra, or galaxy SED. And then the best fit model is this cyan curve is the best fit model, and temperature is 1300 Kelvin. Based on this best fit SED, temperature is this 1300 Kelvin, then the mass is 0.01 solar mass, and then age is something like 50 million years. And if you consider this, it's the magnitude at 4 micron is 27.6 magnitude. So that put this in 5 kiloparsec away. That's very, very far for brown dwarf search. Before, brown dwarf search are several hundred parsec around the sun, but now we are pushing it to 5 kiloparsec. So this is maybe in a thick disk, edge of the thick disk or something like that. To decide the type of L or T or Y, we fit the known brown dwarfs, and then the T dwarf, this 2-1, fit the best. So perhaps we can say this is a T dwarf. And then postage stamp look like this. So it's difficult to see, but in terms of magnitude, 2.7 is faint, and then 4 micron is bright. In terms of number density, we searched for shears and Stefan's quintet and a glass field, so that's about 60 square minute area. And then we found one, right? And then expected number density, from previous estimating Kirkpatrick paper, the estimated brown dwarf number density, and according to that, multiply this volume, and its expected number is 0.15. So this is very small number, but maybe 0.15. If we are lucky, maybe we can find one. So I think this is maybe not so far off from the known number density of the T dwarf. And then this is probably the first time that the T dwarf was found in thick disk. So that's nice. And then she submitted the paper, and then she's working on a referee's comment. Okay, then I can move on to another student.
Yeah, I have a
Yes.
question.
Oh,
how do
teacher,
you-
you're here.
Yeah.
Okay.
How do you confirm that do you have the spectrum?
No, it's 27.6 magnitude, so it's very difficult to take spectra.
In the next slide, are you just seeing the brown dwarf itself and why it was blocking its star or something? I didn't understand what the function is.
Oh, this one?
I didn't. Is that the point from the?
Okay, what
Does
is
it
it?
have a companion star or?
You mean this?
Uh,
That I don't know. I don't know. It maybe. But this is even fainter than our candidate.
I thought that was the star and the associated one was the front.
Okay, ours is at the center, so this one.
Do we expect like a 50 million year object in a thick disk? Isn't it supposed to be like, if you can, the thick disk population is supposed to be like 8-9 giga years old? Do we expect like a 5 million year, 50 million year old object like that?
I don't know. We just did the template fitting and then the best template at this stage. Okay, maybe we can discuss later.
Sure.
I'm not expert in this field. I usually work on galaxies, but this is what we found from the best template. Okay. And then, okay, even more preliminary, but I want to introduce, if there's time, more other students are also doing. So this is another undergrad student, Jacob. He's looking for 3 micron dropouts in Newcomb data. And then, to my surprise, he found some. So here's a 4 micron magnitude against 3 micron minus 4 micron. And then he was looking for object that is undetected in 3 micron or bluer filter, and then only detected in 4 micron filter. And then he found those objects because these are not detected in 3 micron, so this is in a line because of the flux limit of the 3 micron. So this is the only color is only upper limit, so it could be redder than this. But anyway, and then a lot of these objects are garbages, but some of them look real object, promising. So I saw 2 of them. So here it's detected in 4 micron, right? But it's not in any other blue filters, right? And then these objects has more than 2 magnitude difference between 3 micron limited magnitude and 4 micron detection. Then this is another object here. It's detected in 4 micron, maybe something in 4.1 micron, but nothing in bluer band. And then he found some of them. This one may be clearer, so it's bright in 4 micron, right? And then nothing in bluer band, right?
But you also don't see anything. You see like there's a source in the 4.1. But that vanishes when you go to the 444 filter.
I don't know why. That's another interesting object, but maybe in 4 micron filter, this object is bright, so maybe the contrast may be not perfect for this one.
Also, how certain are you about the position? Like we have noticed that within different instruments, there's a slight shift in the astrometry. So how certain are you about the astrometry, especially at such faint targets?
This object is staying at the same position, so
Yes, but
I think
within filters we have seen that the astrometry there could be as large as an offset of about 0.16 arcseconds. So given that we are talking about objects with 0.1 kind of accuracies, how certain are we about the position? Especially in this case where it could be that the 444 there is just some offset and that particular source which is at 410 is basically the same source at 444. It's just that we are positionally offset.
Okay. Well, this is all near ground, right? So it's the same measurement. And then actually Jacob checked the position of detected sources, and then there is actually offset between filters, small offset, and then he corrected for this before doing a match up. I didn't bring the slides to show that. He took like a long time to do that. He took 2 months to do that, something like that. Anyway, so he did that. Thank you for pointing out.
A little bit follow up.
Yes,
So
please.
what's the spatial scale of each cross image here? Like,
I don't know. I don't know. This is probably few seconds, something like that. He should have wrote down the scale. Yes. Okay. So what are these? What do you think are these? If this is Lyman break here, then that's put it to the redshift 30. Or maybe Balmer break, it's a closer redshift. But something like redshift 10 or something like that, Balmer break. But in any case, there are more than 2 magnitudes here, so it's probably there's a chance that there's a break instead of a very dusty slope. So I think it's very interesting object in any case. So that's what he's investigating. I remember. Okay, please.
Yeah, no question. So since you find this dropout, but as a continuous filter of JWST, you could do just the same thing to find dropout in other bands.
Mm-hmm.
And if that's something physical, I will expect you will find a similar dropout in all the bands, right?
Mm-hmm.
Right. So is that being done or?
Yes, that's done.
So you do find in like every set of filters you all find this kind of thing.
Oh, unfortunately, that's done by others. So after JWST data release, the dropouts in 2 micron or 1.5 micron, they're like paper, like 10, 15 papers immediately. So there was no room for our undergrad students to get in there. But then 3 micron dropouts, I don't think many people are doing that because it's uncertain, right?
Right.
As people said, it's only one band detection, so
Yeah,
not
so
many people are.
Then
working on
in
that.
this case, do you see something that happened? You detect it at 410 and 444, but not at
Well,
3.
There might be
56.
this one may have some at 410, don't you think?
Yeah. So you do see in the longer wave wavelength bands, and you do see these kind of things that happen in all the set of bands.
Mm. Well, that's a good point, and then that's a dilemma for me. So of course it's interesting to do 2 micron dropouts or 1.5 micron dropout. That's redshift 15 or something galaxy, right? That's interesting, but I cannot ask my students, undergrad students, to write a paper in 1 day, right? That's impossible, right? So that's a dilemma. I mean, now we're trying to go in a niche direction where not many people are working 3 micron dropouts. But I think it's more uncertain, but I think this is still interesting. Yes, please.
So, your 444 data seems to be much deeper than the 410 or shorter wavelengths.
No, these are brighter. These are brighter. So because of the scaling.
So the sources are extremely bright instead of being deep and even.
Yes, that's right.
The question is, how far is the time difference between these filters?
That I don't know. This is
Can it be just an asteroid?
moving object.
Right.
That's a good question. I should check. I don't know. But these are the first set of the early data release. So I think I don't know. I don't know the time difference. Yeah, I should check.
Sorry, naive question. I'm wondering whether or not cosmic ray will have some imprint on the images.
Well, in principle, these are already combination of multiple exposures.
Oh, I see. Okay.
So hopefully cosmic rays are removed in that process.
But then JWST also has this problem with hot pixels. So how certain are we it's not just one hot pixel?
They did that right.
But even with that, the hot pixel problem, but even if you're dithering, it's like if you have like pretty bright pixels, especially in the early days of the pipeline when
Okay.
there were chances that pixels, hot pixels, escaped, and we are still we're still trying to work out how best to mitigate this. Even with the latest pipeline reductions, you still have these are hot pixels, but these are also transient hot pixels. It might be there in a few frames, and then it vanishes. So it's very difficult for the pipeline to pick it out. So how certain are we that some of these objects are not just hot pixels?
But then when you did that, these hot pixel this position moves, right?
Yes.
So ideally, when they combine multiple exposures, they can be filtered out, right?
So the outlier direction doesn't sometimes catch. I can show you some.
Oh, okay. I want to talk to you afterwards. Yeah. Thank you. Okay. Yes, please.
So in your previous slide, you mentioned that the student actually found quite a few garbages.
Right.
What are those?
Some of the points are that many of those data points are at the edge of the data, like where the data truncated there. So many sources are at the edge of the field. I'm asking him to remove these, remove those edge regions, but he hasn't done that yet. Oh, okay. Now, unfortunately, he's undergrad student and he's coming to NTHU, so he wanted to work with Wade, so he's probably coming here after this one. Okay. Then another student, he's a master student, Leo Lin, is looking at PAH galaxies. Then he selected the ratio 15 micron to 10 micron filter, and then selected very bright galaxies only in 50 micron. And then, as you expect, these galaxies are around redshift 1, because at the redshift 1, 7.7 pH emission line comes into the 50 micron filter, but redshifted twice, right? So, as expected, these are around redshift 1 for the Z. And then he's looking at the properties, and then when he does the acidity fitting, as you see, there's a very luminous PAH emission lines. So those are galaxies he picked up. Then, so these are the postage stamps of PAH galaxies he picked up. And it's difficult to see, but these are bright in 50 micron filter here. Seems like galaxies, I guess, in terms of morphology. Then he plotted this is 7.7 micron pH luminosity against this is total infrared luminosity from the acidity fitting. Then those red one is his galaxies, and then yellow one is Akari galaxies, and then again it's much probing fainter region than Akari galaxies. So here around 10 to the 10 or 11 solar luminosity, so it's becoming to normal galaxies instead of infrared luminous galaxies. Akari is just the U-log and then log, but then now we're probably normal galaxies. And then he was discussing this relation maybe becoming shallower here than the previously known relation for local galaxies. That's what he's want to discuss. Okay. And then another student of mine is picking up obscured AGN. He just did the acidity fitting for all the infrared emitting infrared objects. Did the acidity fitting. Then so that some of the candidates he picked up is here. So when you do the acidity fitting to the JWST data points, and then this component is the AGN warm dust, and then for those two galaxies you have some this warm dust component that is part from the AGN. Posted stamp is something like this. It's very bright in mid infrared, very bright in mid infrared. And then when he plotted the fraction of AGN as a function of redshift for very low luminosity galaxies. So now we're talking about 10 to the 10 to 11, so lower luminosity than U-logs and things. And then he may be, well, still small statistics, so we cannot be sure, but there may be a sign of increase as a function of redshift, the agent fraction as a function of redshift. So that's what he's finding, but this still means working. Okay, I think maybe time to stop. So I introduced many of students' work that the students are doing at NTHU, and I hope I convinced you that even undergrad students can join JWST research. I hope I showed you one example of this. And then, luckily, very fortunately, those three are undergrad, 1, 2, 3. So they decided to come to graduate school. So that was a fortunate story. Okay, I stop here. Thank you very much for listening. Thank you.
Okay, thank you, Thomas.
Thank you very much.
Are there any questions?
Please.
Very much for your interesting talk. So I have two questions.
Okay.
The first is that you have two students working on the number count in two separate fields, right?
Right.
And it looks to me that there seems to be an offset in terms of the number count.
Offset.
So I'm wondering whether it's within uncertainty or it actually comes from the cosmic variance, for example. And if that's the case, how large field in the JWST can observe in order to overcome this cosmic variance?
That's a good question. Actually, there is a little difference in number count. How do I move to the slides? It was actually Lefried's comment to the second student's paper. Maybe I show this one. Okay, so this is just a Stefan's quintet field, but then this Stefan's quintet field has two files, and between these two fields, there's some difference, right? So there are some field-to-field variance in the number counts in the size of the JWST field of view. I think I don't have a plot, but I think something like a 20-30% level between field-to-field variation.
I thought the CS field, the points are kind of systematically higher.
Which one? CS field?
You have a plot with red points.
This one? You mean this comparing this blue and red? Yeah. There's a little bit of field of view variation. So actually, he is looking at this because it was Lefried's comment to his paper, and I think I didn't bring a plot, but I think it was 20-30% level field to field with the size of the JWST MIRI pointing. How much large scale we need to observe this? It's a difficult question because it depends on the redshift, right? So, the size of the field, physical size you require to see large enough scale depends on the redshift. So it's a difficult question that I don't have the answer now.
Okay, and my second question is
Okay.
a bit technical. So in your fit to derive this 20 parameters, do you require that fit is the best solution for all the bands simultaneously, or they are determined separately?
You mean the fit here?
Right.
I guess it's simultaneous fit to all the data, all the filter, plus I should have said plus these previous bits of data too.
Any more questions?
Okay.
Listen, from the cosmic star formation history, fundamentally what you want to constrain is the total infrared luminosity.
Right.
But with JWST, you are actually only constraining the mid-infrared part.
That's right.
You are missing the far infrared, where the bulk of the infrared luminosity comes from.
Right.
Do you think this can be problematic?
Well, but JWST does not find breath.
Right. So you are not, fundamentally you are not constraining the far infrared part, you are just extrapolating your SED from mid-infrared to far infrared.
Right. Well, I mean, I cannot put, JWST is not fine for a telescope, so, okay, well, that's why we wanted to do the speaker. So, that's fine for a telescope, so, but, okay, I can give some comments about that. So mid-infrared is still infrared, so it's still better than the UV or optical for the obscure galaxies. And then some people claim, maybe you don't agree, but there's a correlation, good correlation between mid-infrared and far-infrared. I don't know how good it is, but there is certain correlation, right? So you can guess far-infrared luminosity from mid-infrared. And then, okay, I think we did the best that we can do with mid-infrared data.
Well, I guess this is a good thing to do. You have mid-infrared data, you do some extrapolation to far infrared to get the total infrared luminosity. Just like those far infrared people, they do the brightest source and they make some extrapolation to filter the luminosity. At the end, the two results agree with each other, so maybe that means the two sides are not doing something crazy.
Well, if I could add, so now we're talking about micro-Jansky mid-infrared sources. It's very difficult to detect far-infrared emission of these sources. Even if we have the speaker, we cannot detect these faint sources with 3 meter far-infrared telescope. Okay, please.
So you mentioned in the slide that the number count is, you have a very good match between the right number count and your low luminosity number count. I mean, they match well at that particular intelligence level. So I'm just curious why you don't see the brighter ones, simply because the field of view, or
Sorry, I didn't get the question.
so your number count sort of ends at the mini-Jansky level, right?
Yeah, right.
Yeah, so you don't see the brighter sources. That's simply because in the field of view, which
That's
is
right.
small enough that you don't catch the
Right,
brighter
right.
ones.
Because this is still something like dozens of square arc minutes, so that's pretty small field of view for bright galaxies.
So actually a follow-up on the total infrared luminosity. So I see in the later work you show the SED fitting and put a huge error bar on the total infrared luminosity on both sides. Have you tried to compare the total infrared luminosity of targets with both JWST data and existing far infrared data and see if there's a tendency if the JWST SDV tend to underestimate or overestimate total infrared luminosity?
You're talking about PAH galaxies?
Yeah.
Oh, okay, I see. Well, those with very large errors, they are missing some filters.
Yeah.
Here, right? Yeah, here, not all the galaxies are detected in all the MIRI bands. Then, so those very large errors, they are missing some filters. So that's how the errors become large. And then if it's detected in all the bands, the error bar size is something like this. Well, comparing to fine luminosity observation, it's a good idea, but these are very faint
Yeah.
galaxies. So far infrared observation is also difficult.
Thanks. Are there any more questions? If not, let's thank Tomo again.
Thank you very much.